Yes, it is possible to derate the connected load for a motor control center, or MCC feeder. This implies that you can employ a smaller breaker than the cumulative connected load of the motors. The permissible degree of derating fluctuates contingent on the electrical code in effect. For instance, the National Electrical Code (NEC) sanctions a 25% derating for motor circuits. Consequently, a 400 amp breaker could potentially serve a 410 amp connected load. Nevertheless, several pivotal considerations warrant attention when derating a motor circuit. Firstly, verification is required to ensure that the breaker maintains sufficient capacity to manage the inrush current of the motors. Inrush current constitutes the current surge occurring upon initial motor startup. This surge could attain levels up to 6 times the full load current of the motor. Secondly, confirmation is needed to ascertain that the wires and conduit possess adequate dimensions to accommodate the derated load. These components must facilitate current conduction without inducing overheating. Thirdly, meticulous documentation of the derating process is imperative. This documentation should encompass the connected load, the derated load, and the relevant electrical code being applied. For those uncertain about the appropriate methodology for derating a motor circuit, seeking guidance from a certified electrician is strongly advised. The determination of appropriate conductor sizing and overcurrent protection for motor circuits is governed by specific articles within the National Electrical Code (NEC). These articles provide detailed guidelines to ensure safety and proper operation. Key NEC articles to consult include Article 430, which covers motors, motor circuits, and controllers, and Article 310, which addresses conductors for general wiring. Specifically, NEC Section 430.22 outlines the minimum conductor ampacity for motor circuits, requiring conductors to have an ampacity not less than 125% of the motor's full load current, as determined by NEC tables. This provision ensures that the conductors can safely handle the continuous load imposed by the motor. Furthermore, NEC Section 430.52 details the requirements for motor overcurrent protection, specifying the maximum rating or setting for motor circuit short circuit and ground fault protective devices. The type of motor and the type of overcurrent protection influence the allowable size of the protective device. For example, inverse time circuit breakers typically have a maximum allowable rating of 250% of the motor's full load current, while fuses can have different maximum allowable ratings depending on their type. It is crucial to adhere to these NEC guidelines to prevent motor burnout, conductor overheating, and potential fire hazards. Consulting with a qualified electrical engineer or licensed electrician is essential for accurate application of these code requirements to specific motor installations. The National Electrical Code (NEC) provides specific guidelines for calculating feeder demand loads for multiple motors, which allows for potential derating based on diversity and non-simultaneous operation. NEC Section 430.24 addresses conductors supplying several motors. It states that the conductor ampacity shall not be less than 125% of the full load current rating of the highest rated motor, plus the sum of the full load current ratings of all other motors in the group. This calculation accounts for the fact that not all motors will operate at their full load simultaneously. Furthermore, NEC Section 430.53 provides additional allowances for overcurrent protection of motor circuits. For instance, if the overcurrent device size according to 430.52 is not sufficient to allow the motor to start, the rating can be increased, but not exceeding specific maximums outlined in the code. This provision recognizes that motors draw significantly higher current during starting than during normal operation. To accurately determine the feeder demand load, a load calculation should be performed, considering the duty cycle and operating characteristics of each motor. Factors such as the frequency of starting and stopping, the duration of operation at various loads, and the likelihood of simultaneous operation should be taken into account. If it can be demonstrated that the motors will not operate at their full load simultaneously, the feeder demand load can be reduced accordingly. It is important to maintain detailed documentation of the load calculation and the assumptions made, as this information may be required by electrical inspectors. Consulting with a qualified electrical engineer is recommended to ensure accurate load calculations and compliance with all applicable code requirements. When determining the appropriate size of a circuit breaker for a motor control center (MCC) feeder, several factors must be carefully considered to ensure both safety and reliable operation. Firstly, the total connected load, which is the sum of the full load currents of all the motors served by the feeder, must be calculated. However, simply using the total connected load as the basis for sizing the circuit breaker can lead to oversizing, which can be costly and may not provide adequate protection. The National Electrical Code (NEC) provides guidelines for derating the feeder based on the assumption that not all motors will operate at their full load simultaneously. NEC Section 430.24 allows for the feeder conductors to be sized based on 125% of the full load current of the largest motor, plus the sum of the full load currents of the other motors. This calculation recognizes that the largest motor is likely to have the most significant impact on the feeder load. Additionally, NEC Section 430.62 permits the overcurrent protection device, such as a circuit breaker, to be sized based on the feeder conductor ampacity rather than the total connected load. This provision allows for further derating, provided that the circuit breaker is still capable of protecting the feeder conductors and the motors connected to it. It is important to consider the inrush current of the motors when sizing the circuit breaker. Motors draw significantly higher current during starting than during normal operation, and the circuit breaker must be able to withstand this inrush current without tripping. The NEC allows for the use of inverse time circuit breakers, which are designed to tolerate short duration overloads, such as motor inrush current, without tripping. The specific type and rating of the circuit breaker should be selected based on the motor characteristics and the expected operating conditions. Finally, it is crucial to consult with a qualified electrical engineer or licensed electrician to ensure that the circuit breaker is properly sized and installed in accordance with all applicable codes and standards. They can perform detailed load calculations, assess the motor characteristics, and select the appropriate circuit breaker to provide optimal protection and performance. When determining the appropriate size of conductors for a motor control center (MCC) feeder, it is essential to comply with the National Electrical Code (NEC) and consider the specific characteristics of the motors being served. The NEC provides detailed guidelines for conductor sizing based on the motor full load currents, the duty cycle of the motors, and the ambient temperature. NEC Section 430.22 specifies the minimum conductor ampacity for motor branch circuits, requiring the conductors to have an ampacity not less than 125% of the motor's full load current. This provision ensures that the conductors can safely handle the continuous load imposed by the motor. For feeder conductors supplying multiple motors, NEC Section 430.24 provides additional guidance. It states that the conductor ampacity shall not be less than 125% of the full load current rating of the highest rated motor, plus the sum of the full load current ratings of all other motors in the group. This calculation accounts for the fact that not all motors will operate at their full load simultaneously. In addition to the motor full load currents, the duty cycle of the motors must also be considered. If the motors operate intermittently or have varying loads, the conductor size can be adjusted accordingly. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes, based on the insulation temperature rating and the ambient temperature. It is important to select conductors with an appropriate insulation temperature rating to withstand the expected operating temperatures. The ambient temperature must also be taken into account, as higher ambient temperatures can reduce the ampacity of conductors. Correction factors are provided in NEC Table 310.16 to adjust the ampacity ratings for different ambient temperatures. Furthermore, voltage drop must be considered when selecting conductor sizes, especially for long feeder runs. Excessive voltage drop can reduce motor performance and efficiency. NEC Informational Note Number 2 to Section 210.19, Paragraph A, Number 1 provides guidelines for voltage drop, recommending that the voltage drop on feeder and branch circuits should not exceed 3%. To minimize voltage drop, larger conductor sizes may be required. Finally, it is crucial to consult with a qualified electrical engineer or licensed electrician to ensure that the conductors are properly sized and installed in accordance with all applicable codes and standards. They can perform detailed load calculations, assess the motor characteristics, and select the appropriate conductors to provide optimal performance and safety. When determining the appropriate size of conduit for a motor control center (MCC) feeder, several factors must be considered, including the number and size of conductors, the type of conductors, and the fill requirements of the National Electrical Code (NEC). The NEC provides specific guidelines for conduit fill, which limits the percentage of the conduit cross-sectional area that can be occupied by conductors. NEC Chapter 9, Table 1 specifies the maximum allowable conduit fill for various types of conduit. For example, for 3 or more conductors, the maximum allowable fill is typically 40%. To determine the appropriate conduit size, the total cross-sectional area of all the conductors must be calculated. The cross-sectional area of each conductor can be found in NEC Chapter 9, Table 5. Once the total conductor area is known, the required conduit size can be determined by referring to NEC Chapter 9, Table 4, which provides the dimensions and cross-sectional areas of various types of conduit. It is important to select a conduit size that provides sufficient space for the conductors, while also complying with the NEC fill requirements. In addition to the conductors, any grounding conductors or equipment grounding conductors must also be included in the conduit fill calculation. These conductors are essential for safety and must be properly sized and installed. The type of conduit used can also affect the allowable fill. Different types of conduit have different internal diameters and cross-sectional areas. For example, rigid metal conduit (RMC) typically has a larger internal diameter than electrical metallic tubing (EMT) for the same nominal size. This means that RMC can accommodate more conductors than EMT for the same conduit size. Furthermore, the NEC requires that conduit be installed in a neat and workmanlike manner, with adequate support and protection. Conduit should be securely fastened to walls, ceilings, or other structures to prevent damage or displacement. Finally, it is crucial to consult with a qualified electrical engineer or licensed electrician to ensure that the conduit is properly sized and installed in accordance with all applicable codes and standards. They can perform detailed calculations, assess the conductor characteristics, and select the appropriate conduit to provide optimal performance and safety. Proper documentation is essential when derating a motor circuit or motor control center (MCC) feeder to ensure safety, compliance with the National Electrical Code (NEC), and maintain accurate records for future reference. The documentation should include detailed information about the connected load, the derated load, the calculations used to determine the derated load, and the specific NEC sections that justify the derating. Firstly, the connected load should be clearly documented, including the full load current flow of each motor connected to the feeder. This information can be obtained from the motor nameplates or manufacturer's specifications. The documentation should also include a list of all the motors connected to the feeder, along with their horsepower ratings, voltage ratings, and service factors. Secondly, the derated load should be clearly documented, including the total derated current and the method used to calculate the derated current. The documentation should specify the percentage of derating applied to each motor or group of motors, and the rationale for applying that derating. For example, if the motors are expected to operate at less than their full load capacity, or if they are not expected to operate simultaneously, the derating can be justified based on these factors. Thirdly, the calculations used to determine the derated load should be documented in detail. This documentation should include all the formulas and equations used, as well as the values used for each variable. The calculations should be clear and easy to follow, so that they can be easily verified by others. Fourthly, the specific NEC sections that justify the derating should be referenced in the documentation. This will provide a clear basis for the derating and demonstrate compliance with the NEC. For example, if the derating is based on NEC section 430.24, which allows for derating of feeder conductors based on the diversity of the motor loads, this section should be explicitly referenced in the documentation. In addition to the above information, The documentation should also include the date of the derating, the name of the person who performed the derating, and the signature of a qualified electrical engineer or licensed electrician. This will provide accountability and ensure that the derating was performed by a qualified professional. Finally, the documentation should be kept in a safe and accessible location where it can be easily retrieved for future reference. This will be essential for maintenance, troubleshooting, and future modifications to the motor circuit or MCC feeder. The NEC, specifically Article 430, provides the rules.